In this video, I'm going to go over multi-step conversions with respect to mole conversions in chemistry. But first, let's take a look at dimensional analysis in general. Dimensional analysis is a method that we're going to use in science at large to convert from one unit into a different unit. And we're going to do this using equivalent statements or equivalence statements and this fractional setup to perform these conversions. So if I put an example up here, how many inches are in 1 yard, if we know that 12 inches is equal to 1 foot and 3 feet are equal to 1 yard, you can probably logically do these calculations in your head. But in chemistry, we're going to set these up using fractions to make this a procedure to follow. And this procedure is we're going to start with the unit we know or the amount we know and put it over 1. Right here, we can see I have 1 yard over 1 with no unit because we know we're asking about 1 yard. We'll then multiply that by a fraction. And this fraction has to be equivalent. The numerator and denominator have to be the same value, just with different units. We know that 3 feet equals 1 yard, so we'll arrange it so that 3 feet is in the numerator and 1 yard is in the denominator. And that's because yards here will end up canceling. And I'll show that in just a moment. However, if we stopped here, we'd be at feet. So let's also add another fraction here where feet is on bottom and inches are on the numerator. And we know that 12 inches is equal to 1 foot. If I then canceled units, I would see that yards would cancel out because they're a numerator and denominator. Feet would cancel out because they're a numerator and denominator. And I'm left with inches, which is what the question asked for. Now I just multiply across all the numerators. 1 times 3 times 12 is 36. Multiply across the denominators. 1 times 1 times 1 is 1. And once you get to this combined fraction, just divide. So we get 36, and we're talking about inches here, because that's the only unit that didn't cancel. We're going to apply this same process and this same logic to chemistry. Specifically, we're going to apply it to moles, that concept of how a bunch of atoms all in one kind of pile. And really, we have 3 different conversion factors. And this map is going to help us choose which conversion factor to use. We can see that around the outside of the map, we have in the bottom left, particles, which represents atoms or molecules, any countable thing. Bottom right, we have mass, that would be in grams. That'd be if we used a scale to measure our chemical or whatever. And in the top, we have a volume of gas in liters. We have this on our map because this is a very special relationship. We actually know for real gases, real has a very specific meaning in chemistry, we know the relationship between liters of a gas and moles. This map will be used to kind of chart our path from one unit to another. We're going to be converting between particles, mass, and gas volume in liters, and we'll be using this map. Instead of showing it here, I'm going to show it with 2 examples. Our first example, and this does correspond to our practice, what is the mass of 1.33 times 10 to the 25 molecules of CaCO3, or calcium carbonate? Well, first we'll take our known amount, 1.33 times 10 to the 23 molecules, 10 to the 25 molecules, of calcium carbonate, and we'll put it over 1. Notice that I abbreviated molecules as MC, just to make my life a little easier. Now, if I use my map, I can see that I'm starting at particles here in the bottom left. Because we're talking about molecules, we're talking about a countable thing. I also know, according to my question, I'm asking what the mass is. So I not only know where I start, I know where I have to end up. I'm going to start at particles, convert particles into moles, and then convert moles into mass. And on our map, each green arrow, from particles to moles, each green arrow represents 1 conversion factor. So particles to moles will be 1 conversion factor, and moles to mass will be a second conversion factor. So right now we're at particles, and we need to convert from particles to moles. we can see here that our conversion factor is that 6.02 times 10 to the 23 particles is the same thing as 1 mole. So let's use that as a fraction. I arranged this so that 6.02 times 10 to the 23 molecules is in the denominator, molecules being our particle, and I arranged that so that it will cancel with what came before. But this amount of molecules is equal to 1 mole. If we stopped here, we would be left with moles of calcium carbonate, CaCO3. But we don't want to stop at moles. We want to go from moles to mass. Now notice my conversion factor here, I have to use the molar mass of my compound. Now how do we get molar mass? Well, our periodic table our map tells us we must use our periodic table. I've pulled the entries from the periodic table for calcium, carbon, and oxygen. This compound has 1 calcium atom, 1 carbon atom, and 3 oxygen atoms. I'll plug in the masses from the periodic table, multiply each element, and then add them up. And that number I get tells us the molar mass, which is our mass to mole relationship. It tells us that for every 100.09 grams of calcium carbonate, we have 1 mole of calcium carbonate. Because this is an equivalent statement, we can use this in our dimensional analysis to go from moles to grams. If I head back up to my fractions up here, I'll put 1 mole in the denominator and 100.09 grams in the numerator. So that moles cancels and we're left with grams. Let's actually do that canceling. First, I'll cancel out molecules from numerator and denominator. Next, I'll cancel out moles from numerator and denominator, and I'm left with just grams calcium carbonate. Now for the math, multiply across your numerators, 1.33 times 10 to the 25th times 1 times 100.09. Round it off gets me 1.33 times 10 to the 27th. In the denominator, 1 times 6.02 times 10 to the 23 times 1 just gets me 6.02 times 10 to the 23. And when I divide, I should get 2,211.29 grams of calcium carbonate, because this is the only unit that did not cancel in our dimensional analysis here on the left side. And that is how we would convert from a number of molecules to a mass of some compound. Let's take an example on converting grams into liters of a gas. This problem asks to convert 13.4 grams of CO2 into liters of CO2 at STP. Now notice this says STP. All that means is that our gas is at what we call standard temperature and pressure. It's at the temperature and the pressure where this relationship holds. For our practice, we're going to always assume that the gas is at STP so that this relationship holds. Let's start with 13.4 grams of CO2 over 1. That's the amount we know. We know we're starting at mass and we're trying to convert to moles and then to liters of a gas. That's what the problem's asking for. So start with moles, or mass, to convert from mass to moles. Use that molar mass. We use our periodic table for CNO. We have 1 C atom and 2 oxygen atoms. Plug in the molar masses for carbon and oxygen. Do your multiplication. Add them up. And that's our relationship for the grams of CO2 for every 1 mole of CO2. And we can use this relationship up here to convert. We'll put grams in the denominator to cancel with what came before, the 44.01 grams. And we'll put the 1 mole in the numerator. Now, if we head back to our map, we are at moles right now. We need to convert to gas volume in liters. So let's use that relationship of a gas to a mole. 1 mole equals 22.4 liters of a gas. Set it up in your dimensional analysis so that 1 mole is in the denominator, so that it will cancel. And 22.4 liters is in the numerator. That's what we're looking for. Cancel out your grams, cancel out your moles, and we're left with liters. Multiply across the numerators, 13.4 times 1 times 22.4. gets us 300.16. In the denominator, 1 times 44.01 times 1 just gets us 44.01. Do your division, and you'll find that you get 6.82 liters of CO2, the only unit that didn't cancel. So we're essentially saying that 13.4 grams of CO2 is the same thing as 6.82 liters of CO2. As a quick kind of bonus example, this is not on your practice. I asked the question, how many molecules of CH4 are in 9.22 moles of CH4? Let's start with our first unit over 1, 9.22 moles CH4 over 1. We can see we're starting at moles, and we have to go into molecules here in the bottom left. So let's use our moles to molecules or particles relationship here. Moles goes on bottom, so that will cancel. And the 6.02 times 10 to the 23 molecules goes in the numerator. Now notice that we're actually done. This was a one-step problem. We went from moles to molecules. That was only one step. But we're already at where we need to be. Cancel out moles, multiply across numerators and denominators, divide, and we're already at molecule CH4. So that would be an easier type of example because it only requires one jump, one conversion. Overall, multi-step conversions have a few steps. First, you write your given value and its unit as a fraction over 1. The 1 does not have units because it's not related to some kind of measurement. We use that mole conversion map to see what unit you start with and what unit you need to end with. You write out each conversion factor as fractions. You might have to calculate the molar mass using your periodic table if you're going from mass to moles or vice versa. You then cross out your units diagonally to make sure they line up and they cancel. Multiply your numerators to get a combined numerator. Multiply your denominators to get a combined denominator. And then divide, and that should get you your final answer. I hope this helps you with multi-step conversions.